So having had a look at divisors of integers, and I commented at the time in the previous video that finding divisors of integers is actually quite difficult, we're going to now look at the problem of finding divisors of more than one integer at a time, so-called common divisors. If you've got two integers, a and b, an integer d such that d divides a and divides b, then we call it a common divisor of a and b. It is, as the name suggests, a number that is a divisor of both a and b simultaneously. A close relative of the common divisor is a thing called a common multiple. If you've got two integers a and b, an integer m, say, such that a divides m and b divides m, is known as a common multiple of a and b. So a common divisor divides into a and b, and a common multiple is divided by, can be divided by, both a and b. So that's the difference. We can easily generalize what I've got here to more than two integers, but I'm only going to concentrate on the case of two integers because that really solves most of our problems, or most of the problems that we're interested in. But our first problem, of course, is to find out whether there are such things as common divisors of common multiples. Well, in fact, it's quite easy to see there is such a thing as a common divisor. Every integer can be divided by 1. So for every pair of integers a and b, or in fact any set of integers we like, there's always at least one common divisor, namely 1. And so the set of all common divisors is not empty. And that means it makes sense for us to make the following definition. We take two integers, a and b, not both 0, I'll explain that point in a few minutes, then the positive integer d, such that d divides a and d divides b, so that d is a common divisor of a and b, and that if c divides a and c divides b, then c is less or equal to d. In other words, if c is another common divisor of a and b, it is not any bigger than d, then we call d the greatest common divisor of a and b. And this is the notation we're going to use. We're going to write d is GCD of a and b. In fact, it's quite common to just say GCD rather than greatest common divisor. And I'll do that most of the time during these videos. Now, the definition suggests that the GCD is unique. We've called it the GCD, not a GCD. And in fact, that is the case. But the proof is in the problem sheets for this particular section of the course. So I'll leave you to have a look at that, either in your tutorial or preferably before you get to the appropriate tutorial. So our problem is, how do we find greatest common divisors? Well, we could, in theory, list all the positive divisors of one of the integers, a, say, list them all out and just check them all off to see which one divides into b. And here's an example where we can do that. I'm going to do two examples. Let's look at the GCD of 18 and 30, which I claim is 6. Well, taking 18 as the smaller of the two integers and working out what its divisors are, well, 1 obviously, which again divides 30. 2 is a divisor of 18, that also divides 30. 3 is a divisor of 18, that divides 30. What's the next one up? The next one up is 6. 6 divides 18 and it also divides 30. The next divisor of 18 is 9, which doesn't divide 30. And the only other divisor of 18 there is 18 itself, which doesn't divide 30. Now, of those divisors of 18, clearly 6 is the largest one I found that also divided 30. So that must be the greatest common divisor of 18 and 30. Now, here's another example. The GCD of 35 and 49 I claim is 7. If you want to, pause the video at this point and go through what I've just done. I would suggest you pick 49 as the one to list the divisors of and check off which ones of them divides 35. Well, if you've done that, you'll know the divisors of 49 are 1, 7 and 49, because 49 is just 7 squared. That's why it's an easier number to use. And of those 1, 7, 49, only 1 and 7 divide 35. 7 is the larger of the two, obviously, so 7 is the greatest common divisor of 35 and 49. Well, this is all very fine and good for small integers, but when the integers got larger, listing all the positive divisors would be quite a drag. There'll always ever be a finite number, of course, so you could always do it, but we want to find a more systematic way of doing it. Well, one systematic way of doing it is to use the fundamental theorem of arithmetic that we met in the previous video. You begin to find the GCD of a and b, you write the two numbers a and b as a product of primes, assuming you can do that. Then you look at each prime that appears in either a or b, and you take the lowest power that appears for each prime. Now that could be 0 and typically will be, as you'll see in the examples in a few minutes, What you then do is you take these lowest powers of all the primes that appear in A or B, multiply them together, and that will give you the GCD. So here are two examples. I invite you to pause the video and work out the GCD by the method I've just given you. So you've done that, you'll find that these are the two prime factorizations you want. You find that 6 is 2 times 3, and 21 is 3 times 7. And if you write them out conveniently, using both primes, all three primes I should say, for each of the numbers, there are three primes appearing here, 2, 3 and 7, then what you find, of course, is that 6 is 2 by 3 by 7, 2 to the 1 times 3 to the 1 times 7 to the 0, and 21 is 2 to the 0 times 3 to the 1 times 7 to the 1. And so if you then go through, you pick the lowest power that occurs in each case. Well, GCD should be 2 to the, well, the lowest power of 2 that appears is the 0 in 21. The lowest power of 3 that appears is 1, it appears in both of them. And the lowest power of 7 that appears is 7 to the 0, that's in 6. So you multiply 2 to the 0 by 3 to the 1 by 7 to the 0, and you get 3. And that's the GCD, as is reasonably obvious in this particular example. Now, if you haven't already paused the video and had a go at doing the same thing for 60 and 42, I again invite you to pause the video briefly, write down the prime factorizations, and pull out the GCD of 60 and 42. Now, if you've done that, you will have found that 60 is 2 squared times 3 times 5, it's 4 by 3 by 5, and 42 is 2 by 3 by 7. So you then look at the primes that occur. Well, there's 4 primes this time, 2, 3, 5 and 7. The lowest power of 2 that appears is 2 to the 1, it's in 42. The lowest power of 3 that appears is 3 to the 1, it's in both numbers. The lowest power of 5 that appears is 5 to the 0, which is in 42, or rather not in 42. And the lowest power of 7 that appears is again 7 to the 0, that because 7 is not a factor of 60. So we've just got 2 times 3, so the GCD of 42 and 60 is 6. Now what we want to do is to look at some simple properties of the greatest common divisor. And the first is to note that the GCD of A and B is not affected by the signs of A and B. Why is this? Well, it basically just follows from the fact that divisibility is not affected by the sign. And the key point here is it implies when we want to find the GCD of two integers, positive or negative, we might as well just throw the sign away and just concentrate on GCD for positive integers. Go back to our previous example, we saw the GCD of 6 and 21 was 3. Well, the GCD of minus 6 and 21 will be 3 as well, and the GCD of 6 and minus 21, and the GCD of minus 6 and minus 21. Our second useful property is that the second condition in the definition of GCD, if you care to look back at your notes, which was that if C divides A and C divides B, then C is less than or equal to D, can in fact be replaced by what I'm calling 2 dashed. If C divides A and C divides B, then in fact C must divide D. This is the useful property, in fact, that we could build into the definition, that tells us that all common divisors of A and B must in fact divide the greatest common divisor, not just be less than or equal to it. You'll find a proof of this in the problem set. Our third little useful property is that if A is a positive integer, then the GCD of A and 0 is A. Of course, if A is a negative integer, then the GCD of A and 0 is just the absolute value of A, which follows from the first point I've just made here. Well, this is actually quite a useful result. Let's look at its proof. Well, clearly A must divide A, because A is equal to A, and A divides 0 because, as we saw in the video on divisibility, everything divides 0. So it does follow that A is a common divisor of both A and 0. Is it the greatest common divisor? Well, obviously no integer that's larger than A can possibly divide A, because A is positive, so it follows that A is in fact the greatest common divisor. So that's the proof of our simple little result. The GCD of A and 0 is equal to A. And this result will in fact prove to be very useful when it comes to efficient calculation of GCD, as we'll see in a future video. So having had a brief look at GCD, let's turn to the other thing we were talking about, common multiples. Well, is there such a thing as a common multiple? Yes, clearly. For any integer A and B, then A times B is a common multiple of both A and B. So the set of all common multiples is never empty. It always contains at least AB. So that means we can define the following. If you've got two integers A and B, again, not both 0, the positive integer L, such that A divides L and B divides L, in other words, L is a common multiple of A and B. And if A divides C and B divides C, then C must be bigger than or equal to L. In other words, every other number that's a common multiple of A and B must be at least as big as L, can't be less than L. That's called the least common multiple of A and B. And this is the notation we use. We use the notation that L is LCM of A and B for the least common multiple of A and B. Again, our definition implies that the LCM is unique, just as the GCD is. This, in fact, is quite easy to prove. I'm going to prove a little result that will allow us to just knock that one off very quickly in a few minutes. So how do we find the LCM? Well, if we try to list all positive common multiples of A and B and choose the smallest, well, that's not really a sensible way forward because there are infinitely many common multiples, AB, 2AB, 3AB, 4AB, just to start with. So that's not going to help us. But as in the case of the greatest common divisor, we can actually use the fundamental theorem of arithmetic to calculate the least common multiple by writing A and B as a product of primes. And rather than taking the lowest power of each prime that occurs, we take the highest power and multiply these highest powers together, and that will give us the least common multiple. So here's the same two pairs of numbers that we met in example 4. I invite you to pause the video, and you can use what we did in example 4 to write down the LCM. Well, going through this in detail, once again, 6 was 2 by 3, remember, 21 was 3 by 7. We write these once again in terms of all three primes that occur. 6 is 2 to the 1, 3 to the 1, 7 to the 0. 21 is 2 to the 0, 3 to the 1, 7 to the 1. So the LCM must be 2 to the 1 because it's the highest power of 2 that occurs. It's in 6. 3 to the 1 is the highest power of 3 that occurs. It's in both numbers. And then 7 to the 1 because that's the highest power of 7 that appears, and that's in 21. And 2 by 3 by 7 is 42. Okay. Now if you haven't already tried that with 1642, again, I invite you to pause the video and do so. This is what we should have got. We already saw 60 is 2 squared by 3 by 5, and 42 is 2 by 3 by 7. So it must follow that the LCM of 42 and 60 is 2 squared, because it's the highest power of 2 that occurs, by 3, by 5, by 7, and that turns out to be 420. Now, of these two concepts, the GCD turns out to be much more important than the LCM. We use the GCD a lot more than we use the LCM in applications. But in fact, they're very closely linked. If you can find one, you can find the other. But this theorem tells us that for all positive integers A and B, the product of the greatest common divisor and the least common multiple is always AB. If A and B are not positive, then you have to put absolute value signs on here. But that's the only difference. And this is quite easy to prove. If you multiply the GCD and the LCM together, well, if you look at all the prime factors that there are of A and B, the lowest power that appears in the GCD and the highest power that occurs in the LCM. There are only two numbers, so either the appropriate prime power has gone into the GCD or the LCM. So if you multiply all of them together, you in fact get each prime factor to exactly the correct power for A times B. And that's the proof. Furthermore, if we knew the GCD were unique, then this result tells us that the LCM must be unique as well. There's only one GCD, there's only one AB, there must only be one LCM. So once we've proved uniqueness of GCD, which you should do in the tutorials, then you've got the uniqueness of the LCM. The other thing this tells us is that if we actually want to work on GCDs and LCMs, we only need to calculate one of them, and in fact it's the GCD we concentrate on. As I've just said, that's actually rather more important. So once we know a quick way to find the GCD, we know a quick way of finding the least common multiple, we just divide the product AB by the GCD, and that gives us the least common multiple. Now, as I said in the previous video, actually factorizing numbers is hard, so given two large numbers, finding the prime factorization is going to be a very big job, and if all we could do to find the GCD were to use the prime factorization, well, we'd be in for a lot of work. We would literally be in for twice the amount of work we'd be involved in just factorizing one number. But fortunately, there's a much quicker way of finding the GCD of two numbers than finding the two prime factorizations. That's what we're going to be looking at in a future video. But before we do that, we have to have a closer look at what happens, another look at divisibility, what happens when one integer doesn't exactly divide another. And that's the subject of our next video on quotient and remainder.